Today's session is all about 3D engraving on the laser machine. Now, whether you've got a diode laser, an RF laser, or a CO2 glass tube laser, it makes no difference. This 3D-ness is something that we can all achieve. Now, what is 3D? Now, 3D is what my face is. I know it's ugly, but it's still 3D. Everything around you is 3D. But the thing is, your eyes are not 3D. They may physically be 3D, but you've only got stereoscopic vision. You do not have 3D vision. 3D is something that your brain creates. It tells you the relative distance of things, and you store pictures of what you can't see. Now, there are times when we can believe our eyes completely, and other times our eyes will actually lie to us. Let me give you a simple example. I walked past my wife's wardrobe a few days ago, and I saw a lovely little black dress hanging in there, and I said to her, "That's a lovely dress, I haven't seen that before." "Oh, I've had that ages, dear," she said. "I wore that for Maxine's wedding." "What, with the price ticket on it?" Now, that's believing your eyes. I'm going to show you something that is not quite the same sort of thing. We know what this is. This is a tin. It's round, and obviously you know that it's round. How do you know that it's round? Well, to be honest, you don't, because that could be a picture. The only reason you know that it's round is because of experience tells you that something that looks like this, and the fact that I can go like this behind it, tells you that there's something behind there. You can't see behind there. You don't have 3D vision. You have 2D vision, which basically stops just there, where it disappears around the corner. You can't read what that label says around the back of the tin. You have 3D perception based on experience, life experience. Right, so here we are. It's that same tin. Look, there it is. It's on my TV, it's on my monitor. That's how your brain can fool you. An artist can obviously draw what's on that screen, and it can give the impression of being 3D, even though it's not. Now, all the clues about that being 3D are in that image. Things like the shadow, things like the shape and how it's got perspective and it disappears into the distance. That's not a 3D object. It's a picture of a 3D object. Now, that's a very important concept to remember when we're talking about 3D-ness on our laser machines. I've seen people on YouTube videos thinking that this is a 3D image. There are lots of clues in there that give you an impression that there's depth to that because of the way in which it's shaded. That's a picture of a 3D image, not a 3D image. When we go onto Etsy, we find this model is available it's a 3D STL model. Now, STL stands for stereolithography. Some people call it standard triangular language. But that's a language which is a mathematical definition in space of 3D. So that's what standard triangular language looks like. It's a triangular mesh that stretches over the surface of a 3D object, and each one of the triangular points is defined mathematically, not as a bitmap. It's got 3D-ness encoded into the mathematical code. But there is some further clever software around which will enable you to turn that mesh into a visualization, a 3D visualization. So that's a rendering of that mesh. And you'll notice it's got highlights in the foreground, shadow under there. This is still a 2D rendition of a 3D model. It's a picture, it's a photograph. It's not a 3D model. Well, let's change the subject and take a quick look at a survey map. And we can see that they have got 3D-ness to them. Even though this is a 2D image, we imagine what's going on behind the green hill there. But we can't see it until we project it down onto a 2D map. And what we've done there, we've taken slices through the mountains, we've projected those slice shapes down onto a flat 2D surface. This is a topographical map. We can take 256 slices through there. So from a background plane, we can use the grayscale code to encode this dimension here, the Z dimension. Let's just see how that works in practice. And there it is. Yeah, okay, it looks realistic, but it doesn't look 3D because all the normal clues that your eye wants to look for are not there. It looks weird. But that image contains all the 3D information that we need to produce a proper 3D image replication onto a piece of flat board. We can dig deeper and deeper and deeper with our black, leaving the white on the surface. Now, I'll give you a demonstration of that in the workshop soon. Basically, we've got black 0, white 255, and all these various shades of grey in between are the slices which give us the 3D information that we need. That's completely different to that image there. There is no 3D-ness in there when you look at it. It's the same as that photograph. Okay, so just a final word on STL files. I've been to the NASA website and I've picked up an STL file, which is a 3D file. This is not the mesh, this is the final rendered result with artificial light on it, etc. Now you can see that it's artificial light because look, you've got this light coming in from the direction of the N, and you can see the shadows being cast all the way across. So there's our 3D image that is going into our brain, making us believe that this is a 3D image, even though it's on a 2D screen. But I've noticed something rather interesting about this. When I rotate this round, the light, which previously was here, is no longer here. The shadows that were there are still there because the light is over here. But hang on, look at the highlight. The highlight is on the same side as the shadow. I think there's something wrong with the software here. So I went online and I converted this file from STL to PNG so that it could be put into a Lightburn. That would not produce a proper 3D image. It would produce a bumpy image of some sort, but not a proper 3D image. There's another picture there, for example. That doesn't look anything like that bunch of flowers that I just showed you. Yes, we've got some very contrasty whites and blacks, but this is not a photograph. This is a manufactured image, and the manufactured images have got very sharp edges. And look, we can do artificial lighting on it and we can do different shadings. This will come out as quite a reasonable 3D image because it's got colour information, contrasting colours in it, which will pick up different depths. But it's still not going to be a proper 3D image. I recently did a video about the myths and misunderstanding of what you see on the screen there, the material matrix test. Now you can go into Lightburn and you can automatically pre-create one of these matrix tests for yourself. And there are hundreds of videos out there which show you how to do it and why it is so important for new people to understand what the best settings are for their machine. What is the best setting? If you're doing photo engraving, you don't need this at all. There are completely different techniques for determining what your speed and power should be. And if you're doing grayscale engraving of photos, well, look, here's what dark looks like, and here's what white looks like. Can you imagine trying to grayscale engrave on a piece of thin card when that's black? There are three important things that you must understand before you start putting laser to material when you're doing 3D engraving. The first thing is your lens. What is it capable of doing? Now I'm going to illustrate that to you in a few seconds by taking some little edits from this video that I've got here and showing you the effect that your lens has on materials. Now the next thing is the material itself. This is wood, which is an organic material, which will vaporize under the influence of your concentrated laser beam. You can see that it's vaporized material here because look, we've got different depths of material that are missing as we change the power of the laser. It hasn't burnt it away, it's vaporized it away. Now this effect happens regardless of the laser type that you've got. All lasers concentrate the beam with a lens. whether it's a diode laser or whether it's a CO2 laser. So this problem is exactly the same for all lasers. The diode laser will have less effect on wood than the CO2 laser, but that's purely because of the wavelength of the light. Certain materials will 3D engrave and others won't. Here we've got a material that is capable of being vaporized. Things like stone, slate, glass are not capable of being vaporized because they're mineral materials. So you can't 3D engrave on those materials. The final thing that you've got to consider is, what is your machine capable of doing? Now, the CO2 laser is less capable than a diode laser when it comes to doing 3D engraving, and I will explain that later on. But let's just jump into the first problem, which is the lens, what it can do and how it affects material. And I hope you can see that that beam is not uniform. It's very bright in the centre and it drops away to almost nothing at the edge. That is what our laser beam is like, whether it be a diode laser or whether it be a CO2 laser. It's a characteristic of the laser beam. We've got a very, very small central intensity which has gone right the way through the centre and burnt a hole there. But look what the low intensity's done. It's put a scorch mark, a big scorch mark, around the outside of this high intensity hole. The paper is thin, so the high intensity burns its way through the hole very quickly in 2 milliseconds. That's all it took to do that amount of damage. Here we've got a lovely piece of Baltic birch plywood. It's quite light to keep the speed similar to those that you're going to get on a diode machine. I've got this set to 100 millimeters a second. That's 6,000 millimeters a minute. So 95, 80, 70, 60, 50, 40, 30, 20. So we've got nearly 70 watts here, but it's an unfocused beam. This is the raw beam. Something else that you may notice if you look carefully, we've got no colour change, but we've got change of line thickness and deeper cut. Okay, so we're going to run that same test again, but this time 3,000 millimeters a minute, 50 millimeters a second. By slowing it down, we've got a slightly darker shade of brown. Still not black. There is no colour change because we've changed the power. What we've got in there is a 2.5 inch focal length lens. We're going to run this at the same speed that we did previously, which is 50 millimeters a second. Now, I'm using exactly the same program that I used a few seconds ago. I've just squashed it down. It's running between 15 and 95% power. Now, look, I put this test piece over the top of our previous test piece because they are both running at between 15 and 95% power. This one is the raw beam, and this one has been passed through a 2.5 inch lens to concentrate it. It's the same beam running at the same speed with the same amount of power in the profiles, and you'll notice that the line width does subtly get wider as the power increases, but as the lines get thicker they're not changing the blackness, they're all exactly the same colour black. Why would that be when we're increasing the power? Let's just have a look at the edge if I can. They are cuts, even at 15% with that thin line. Look how deep we've managed to cut the very first line. So if I reduce the speed, because I can't change the power, I've already got the power in this pattern set up to 100% at the top here, nearly 50 millimeters a second, and this one was 30 millimeters a second. What's the difference in colour between those two samples? They're all roughly black, as opposed to brown when we had no lens in. Are your eyes deceiving you? Are they really black? Let's just have a look. It's very definitely black. Or is it? Let's take the next one off. It's not black. But I can make it black by doing that. It's an optical illusion. If you can't get light into somewhere, you can't reflect the true colour of what's inside. Your eyes are deceiving you. These black lines are not black at all. It's occlusion of light that appears to make them black. Okay, now I'm not going to change anything about this test, except I'm going to close the line spacing up. On the left we've got two thin lines, and that means we get more white between the lines. As the lines get darker and thicker, the gap closes down. We're all of a sudden starting to see some colour coming into this. Look, I've changed nothing except the spacing between the lines. Let me close it down just a little bit more, and look, all of a sudden we appear to be seeing black. But we know we're not seeing black. We've got the same lines that we had here that were not black. But you'll notice on the left hand side we still have some light brown, because the spacing between these lines is different to the spacing between these lines, because remember, as the power increases, so the line thickness increases. We'll go down one more step, and look, we've produced black. Wow, isn't that amazing? You ought to look at it from the other direction. We've gone in there and we've produced a series of very, very deep cuts. Now bear in mind, these are not all the same power as you would normally do. This is a special program where I've got varying power. What we're finding is, at this last part of the cut, we are actually cutting below the surface, whereas previously they're all the same height, and it's not quite interfering with the next cut. Unlike a drill, a laser beam does not cut uniformly. There is a very high intensity part to the beam, which is at the center core of the beam. The higher the intensity, the faster damage will occur. The lower the intensity, the slower damage will occur. That first hole illustrates the very high intensity core, and it also shows the lower intensity, less damaging part of the beam, which is the outer part, and that causes scorching as opposed to vaporization. Let's put that into context with what we've just seen. Here we can see uniform spaced cuts, but if you look at the shape of the cut, you'll see that it is conical at the top. The central core of the beam is cutting deeply and almost uniformly parallel into the material, and that lower power around the outside of the central core is causing a conical damage. It's producing damage at a slower rate. So here we've got exactly the same power and exactly the same beam, but this time the gap has closed up. So consequently, our scorched outer parts of the beam are now beginning to overlap. They're still able to produce some vaporization, and look, they've vaporized this below the surface of the material, and it's left a scorched black mark on the wood. Now, the whole point of 3D engraving is we want to remove material, but we don't want to scorch the material. Look, if you were producing a 3D engraving on a milling machine in wood, the surface of the wood would be exactly the same colour as the wood that was maybe 3 or 4 millimetres deep. You wouldn't get black at the bottom of a cut if you were doing it on a milling machine. That's 3D engraving. That's what we're trying to emulate. The fact that we might be able to get colour into the cut is an interesting possibility, but it has to be done with knowledge and understanding, not by accident. So that's why I'm explaining all this detail to you, to show you where the colour comes from. The bit that we're interested in is removing material for 3D engraving. But you can see, if you're not careful, as a consequence of removing material, you're going to produce charcoal. And if you look at a lot of people that do 3D engraving, they say, well, yeah, this looks okay at the moment, but it'll look a lot better when I clean it up with water and a toothbrush or something like that. Okay, what they're really doing is removing the char burnt surface. How much better it would be to not have the charred burnt surface to start with. So now we come back to this matrix test. And look, we can see that where we've really gone very deep, we've probably got a load of combs in the bottom there, which are going to break off. And all this is tar. This is not scorching. This is not the scorch effect. This is actual physical debris that's come out of the wood, the tarry residue, the fumes. But if we look over here, what we're really trying to find out from this matrix test is what's the most efficient speed and power for this lens. Change the lens and it'll vary. This is a 2.5 lens, which is, if you like, my choice of lens that I would use for 3D engraving. So we've got hardly any colour change here on this one, but we've got very little depth penetration. You know, that one looks quite a nice depth, probably 0.5 millimetre, which means we could get 3 millimetre in 6 cuts. It's not terribly different to the background colour. We haven't got a horrible brown muck. We've got 0.5 millimetre deep, and I would say that at 65% 400, we've probably got nearly as much depth without much colour. Would I run at 200 millimetres a second or 400 millimetres a second? Well, it makes obvious sense. I'll go a lot faster and do this job quicker if I can run at 400 millimetres a second. So this helps me to decide will be 65% at a speed of 400. At 400 millimetres a second, somewhere between maybe 12 or 14%. Maybe my minimum power. This matrix test has got real value when we're starting to work with 3D. The image that I've chosen is a very high quality image at 300 dots per inch. And it's quite a big picture, so I had to shrink it down to something that was reasonable for me to print, and I'm using poplar plywood, which is a nice white material. So I've loaded this into Lightburn, and let's go and have a look at the settings that I'm using. There's my image, 300 ppi, which means it's basically going to have, and Lightburn does this for you, but if you divide 25.4 millimeters by 300 dpi or ppi, the dot size that you're going to put down for each one of the pixels that are on the screen. I'm using a CO2 laser, which means I need a 0.08 dot to match that requirement basically, and I'm promised that I can get that from a 1.5 inch lens. The 1.5 inch lens says the average spot size is 0.075, so I should easily make 0.08. You guys with diode lasers are going to be suffering a little bit more, because if you believe what your lens manufacturer tells you, or what your machine spec says, it says you can do 0.08 also. The problem is your dot is not round. Your dot is ovalish, and it is roughly 2:1 ratio width to length. So you're going to finish up with a 0.08 dot that's 0.16 wide. Now that represents a problem, but hey, let's just discount that problem for the moment and just stay with my very simple 0.08 dot. Here's what my settings are. Currently I'm running with a speed of 400 millimeters a second and 50% power and 50% power on a 70 watt tube. In my early days I thought, well, if I'm going to go that fast, then I need quite a lot of power to put me dots down. So that's where I started. Here we've got our 0.0847, 300 pixels per inch, 300 dots per inch, and I'm using the Jarvis dither. I used to rely on the Photoshop dither because I thought it was a pretty clean Floyd Steinberg dither, and when I compared what Photoshop was doing with what Lightburn was doing, basically Lightburn and Photoshop are both using the Jarvis dither. This is about as good as you can get, Jarvis. Now, as a first attempt at my photo engraving, I'd say, well, that's not bad. But in fact, it's pretty crap. Why? Well, let's have a look. First of all, I run my finger across it, and this bit is smooth, and this bit is all rough. And not only is it rough, it's also 3D. By 3D, I mean, look at those middle of the eyes there. Those are sunk in. The holes in the nose are sunk in because they're black, and black cuts deeper. Or does it? Well, no, it doesn't cut deeper at all because we've got dots on here. Every dot is the same size as every other dot, so there is no colour difference between different dots. So why have I got a 3D image? I mean, this bit here is pretty smooth. There's no 3D-ness on this background. Right? You can look, you can hear the difference. And now what I'll also do is this, probably, and maybe this will give you a clue as what's going on. You see what I mean? what we've got is little mini combs in there, those things that I demonstrated to you earlier. We've got overlapping cuts which are producing a comb effect, and you're producing scorching on the surface of the combs. And look, I can scrape them off. I can't scrape these off because, let's go and have a look at those under the microscope and we'll explain the difference between this and this. You know what that is because I've already shown you. Now, I'm looking at the light smooth part of that job where I can see individual pixels, and my individual dots here look to be around about 0.15 diameter, which is twice what I was promised. So we've got a problem to start with. As soon as I start overlapping those dots in the dark area, we're putting a double burn on it, half from one side and half from the other side, and that's producing a deep burn. We're also producing lots of tar on the surface. Remember what we talked about, the comb effect? Well, when I scrape the comb off, look at the difference between that area there and this area here where I scraped it. We're nearly back to bare wood. But the point of that exercise is to show that the colour has got nothing to do with the number of dots. It's the overlapping of the dots and the scorches at the edge of the beam which are causing this darkening and this overburning. Okay, when we reduce the power, we get a lighter picture, but we've still got 3D-ness in there. You've only got to rub your fingers across it and you can feel it's 3D, apart from the roughness of the surface. Okay, so whichever way we do this, we've produced accidental 3D-ness, which we don't need because a photograph does not have any deviation in its surface. It should be perfectly smooth, and that's the way you can tell whether you've got your dot size correct. You will feel no roughness of the surface. It will feel all lovely and smooth like this. So let's go back and we'll change the resolution of this picture now to something different. Right, well, I've now changed the speed to 200, half the speed. I've dropped the power to 20%, from 300 to 150 pixels per inch. Hopefully I've slowed it down so that the machine can keep pace with it. But by dropping the speed, I've also dropped the power so that I don't overburn the pixels or make the pixels too big, because I'm still using a 1.5-inch lens, which has got quite a big dot size. I don't want to go too far into photo engraving, which is technically what we're doing here, because we've got a dithered image. I've reduced the dither to match more or less the size of the capability of my machine at the moment. So, and what I find is I've got nearly a flat image. It's still not completely 3D. This black here is still a little bit rough. This black here between the two light areas is definitely a ridge, only a very slight ridge, but if you close your eyes and just rub your finger across it, you will feel it very easily whether it's 3D. So this is getting much closer towards a proper photo replication. Now look, as you see, I've done absolutely nothing to this image at all. It's not been lightened, it's not been sharpened. This is the photo. I've just dithered it. And if you dither a photo properly and understand what your machine is doing, you can get good photo replication. That's not the purpose of today's exercise. Today's exercise is to show how you get accidental 3D-ness out of having dots or lines that overlap each other. And it's the lines that overlap each other that cause the burning effect that I tried to demonstrate to you early. Now that's very important when we come to do 3D engraving. We will now just turn this image into a grayscale image. Right, now I'm going to stop there. I don't want to do the whole thing, and what we'll do, we'll just run it again, because that's the whole point of grayscale engraving. You run it several times so you can get depth into the product. Okay, now I've already got, actually there's not too much depth there. It is grayscale, but look at the quality of it, it's rubbish. You can see that we're taking material off, probably only about 0.2, because I'm not hitting it that hard, because I've got a very sharp lens on there, a 1.5-inch lens. But we've definitely got big holes here and here where the black is and where his nose is. So this is exactly the opposite of what you'd expect a 3D image to be. His nose should be up in the air. This is not 3D engraving. This is accidental 3D-ness because of lack of understanding of what's going on. We're now doing a proper 3D bitmap, and we're already, with our power at 65%, we're taking off roughly, I think, probably 3/4 of a millimetre, and we've gone through the first ply on this piece of plywood. 400, 65% power is what we decided we could do with the matrix burn test, and those are the parameters that I'm using here. Now we're going to have to leave this cooking for several passes, maybe 5 or 6 passes. That's one of the great advantages that light burn has got, is that I can just change this to 5, set it going again and walk away from it. Now engraving is not dangerous. You can walk away from engraving. You cannot ever walk away from cutting. Without even trying, or even on the first pass, we've got something that's beginning to look 3D-ish and a bit more realistic than the dog, because things are working the right way round. The background is disappearing deeper and the foreground is staying in the foreground. We've just come across the internal plies not joining up, and that's what that gap is. So I think what we'll do, we'll stop this and we'll rerun it in a much more homogeneous material like acrylic. This is done on white acrylic because there is no grain in white acrylic to interfere with the pattern. This is cut number 6. The first 2 cuts were done horizontally and the last 4 cuts are being done vertically. They're all being done at 200 millimeters a second with 10 and 65% power using a 2.5-inch focal length lens. The focus was lifted up 4 millimeters before I started. Now the depth of cut is approximately 4 millimeters, so that means at the bottom of that cut we're now 8 millimeters out of focus. Now I think the lesson that you must take away from this is there is only one type of file that allows you to do a bitmap like this. The STL files will all basically be photographs, pictures of this. They cannot produce 3D, proper 3D. They may produce a 3D-ness, but it's nothing like this. As soon as you put an STL file through something like ImageR, you're immediately turning into a dithered file, which is a flat picture with features that fool your eye into thinking it's sort of 3D, but it's not proper 3D. And we move the light around. So you can see the 3D-ness of the object. And there is another way to view this as well, which looks pretty cool, with a backlight. Well, thank you very much for your time and your patience. I hope this has been a rewarding session, and it's cleared up some of the problems that people seem to be having with 3D engraving and 3D-ness. They're not the same things.